We learned in the previous lecture that the direction of the E field, the direction of the B field, and the direction of propagation of the electromagnetic wave are mutually perpendicular to each other, and the wave propagates on the direction of E cross B, as you can see from this diagram. So, suppose I write an expression for the electric field, okay, which is in the form of a wave, and in particular I want to write it down in form of a sinusoidal wave. This is the simplest case, simple harmonic wave. So I'm going to basically write E as a function of x and t. You notice it is not a function of y and z, because that is the definition of a plane wave. Okay, within the y and z plane, the electric field is uniform, but it depends on the x direction. So this is a wave that propagates along the x direction as a sign of cosine function. So what I'm going to do is I first write down the amplitude of the E field, which is E maximum. Okay, and I'm going to write sine kx minus omega t. You know, this is a typical way of writing down a sine cosine wave, right? The argument, the phase angle kx minus omega t. K, as you recall, wave, and omega is frequency. Since I wrote x here, you know, this is a wave propagating along positive x direction, as we see from this diagram, and it is in a y direction. Okay, it points in the y direction, the E vector. So I'm going to write j here. That's the unit vector along the y direction. What I want to know is, if I have this electric field, what must be the accompanying magnetic field? Okay, the magnetic field must exist. We learned before, you cannot possibly have only an electric field, and conversely, you cannot possibly have a magnetic field. So I want to write down the corresponding magnetic component of this EM wave from the expression of this electric field. And the way I do that is by solving the equation relating E and B. Actually, there are two equations relating E and B. You can either take gradient cross B equals negative partial E partial T, or you can go with the other equation, gradient cross E. Gradient cross E. Now, what is that equal to? Okay, that in fact is Faraday's law of induction. It is negative partial B partial T. Remember that? Okay, that's Faraday's law of induction. So what I'm going to do is plug this value of E into here, and then I'm going to solve for B. Okay, it's relatively simple to do. This gradient cross, this gradient operator, as you know, is I partial x plus j partial y, and then plus k partial z. When you operate this on the electric field, remember the electric field depends only on x. It's not a function of y and z. Therefore, I don't have to worry about partial y and partial z. I only have this term. Okay, I partial x. So I have I partial x cross E. E is right here. E maximum sine kx minus omega t j. That is the left hand side, and the right hand side equals negative partial b partial t. Okay, now let's work on the left hand side a little bit more. First of all, the direction is I cross j, so the direction is k. So b is in a d direction with a unit vector of k, and that of course is expected. So what's left is E maximum. Okay, unit vector k along the z direction, and then partial x of sine kx minus omega t. Now if you do that, you get k cosine, right? And then kx minus omega t, right? You take a derivative of sine, you get cosine. Okay, now please do not confuse these two k's. This k is the wave vector 2 pi over lambda, and this is the unit vector along the z direction. Okay, so please do not confuse these two. It equals negative partial b partial t. That tells us, first of all, b is in a k direction, it's z direction, and secondly, b must also assume a sinusoidal form. In fact, b is a sine function of time, just like E. Then when you take partial t, you can turn it into a cosine function. Okay, so b really as a function of x and t should be b maximum sine kx minus omega t. As a matter of fact, we can find what B maximum is by plugging this into here. Plug this expression for B into here. Then I get, okay, the right hand side is now the right hand is equal to negative B maximum. Okay, take time derivative with respect to this of this function with respect to time, negative omega. So there's a positive, right, omega, and then cosine kx minus omega t. All right, so this is the left hand side, and that is the right hand side. Right? They should be equal. So you have a cosine kx minus omega t on both sides, so that nicely cancel out. So they're both in the z direction. But what's left is E maximum times k on this side and B maximum times omega. So you conclude that to match them, I have E minus times the wave vector k must equal to B maximum times what? Omega. And therefore, the amplitude of the magnetic field B maximum must equal to k over omega times E maximum. What exactly is k over omega? Well, as a matter of fact, if you do not remember exactly what is equal to, we can easily derive this once we know what k means and what omega means. K over omega is 2 pi over lambda. Lambda, if the wavelength, right, that's k, divided by omega. Now, omega is 2 pi times the frequency f, right? So this really is 1 over lambda f. Lambda times f is what? Is the speed of the wave. In this case, it's the speed of light, c. So it's 1 over c, okay? And so therefore, we conclude that B maximum must be equal to E maximum over c, okay? This explicitly relates the amplitude of the B field with the amplitude of the E field in a plane electromagnetic wave. So once again, it's clear that E and B must coexist because one is 0, the other must be 0. Okay, so you see, E and B have the exact same phase angle of kx minus omega t, so they should go up and down from minimum to maximum and back to minimum simultaneously, and their magnitudes, their amplitudes are related by that. You notice C is a very large number in SI units, therefore B, the amplitude of B, is much smaller numerically than the amplitude of E in SI system. That is consistent with the fact that Tesla is a large unit. Okay, in the SI system, it's a large unit. So that's why we have a much smaller value of B in Tesla versus a much greater value of the electric field in Newton per Coulomb. Now, does that mean that electric energy carried by the wave is far greater than the magnetic energy? No, it doesn't. Okay, because the choice of units from, say, Tesla to Gauss, for example, can actually numerically enhance the B field without actually changing its actual value. So what really matters is not, it's a very small value in Tesla, there's a very large value in Newton per Coulomb. What really matters is how much energy is carried by the B field and the E field. Okay, we'll see that in just a minute. But let's box these results, B and E. Okay, again, there is no phase difference between the electric and magnetic components of the electromagnetic wave. Okay, you see they have exactly the same phase. So if I were to draw a picture, a visual picture of the electromagnetic wave at a given moment of time, okay, what would I get? Well, at this very moment of time, if the electric field looks like this, it's a sine wave, right? In a y direction, so it looks like this. Okay, and as a matter of fact, I can put some more arrows to give you a more visual idea of what the electric field looks like. Okay, so at this very moment, the electric field at various locations on the x-axis will look like this, and at the very same moment, what about the magnetic field? Well, the magnetic field reaches maximum at the same moment when the electric field reaches maximum. So the magnetic field which points along the z direction will look like this. Okay, at this very moment, it will look like this. So when the electric field goes to maximum, the magnetic field also goes to maximum, and so on. So I'm going to draw some green arrows to indicate the magnetic field values at various locations at this moment. Okay, so you see, for example, at this location, both E and B reach maximum value, and that location they both reach 0, and at this location both reach maximum, and then go back to 0 simultaneously again, and so on and so forth. So this is some sort of visual picture, okay, of a plane electromagnetic wave with both E and B components. Okay, like I said, it doesn't matter numerically that B maximum is a lot less than E maximum. This is based on how we choose such units such as Tesla and Newton per Coulomb. What really matters is how much energy they carry. So let us now study the energy carried by an electromagnetic wave. Okay. Now suppose I look at the cross section of area A that is perpendicular to the direction of propagation. Okay, and of course, if I count the energy passing through this window, more energy will pass through it if I count that over a longer time. Now, what really matters is how much energy passes through this window per unit time, okay, or over a certain time interval t. All right, so let's look at the time interval t. Let's count just how much energy is of the electromagnetic wave passes through this window of cross-section area A. Now it is clear that all the energies that make the wave pass through this window over time t, okay, all the wave passing through this must already reside within this volume, and the length of this volume is c times t, because the wave travels at a speed c, and therefore at a time t later, a wave that's originally here can barely make its way through the window, and therefore all I need to do really is to count just how much energy is contained within this box, okay, of cross-sectional area A at height ct. Now the volume, of course, we know is A times c times t, right? So what we really need to know next is what is the energy per unit volume, energy density otherwise, right? If I know the energy density, then all I have to do is multiply this by the volume. Then I find total much, all this energy contained in the box, and all this energy will pass through this window over time t, okay? So, what is the energy density? Well, there are two forms of energies, electrical energy and magnetic energy. Okay, the electrical energy, UE, the energy density for electrical energy is 1/2 epsilon naught E squared. All right, E squared. Now, the trouble is, E is not a constant. It is not uniform from place to place, right? But what I want to know is what is the average value of E over space. Okay, because then if I find the average value of E over space, actually average value of E squared over space, then I multiply this by the volume, I will get the total amount of electrical energy, right? So I'm going to have to average it over space. Okay, I'm going to average it over space. Okay, now E is a sine function of space. It's sine kx minus omega t. So what you need to do then is to do this, 1/2 epsilon naught E maximum squared sine kx minus omega t squared, and then you have to average it over space. In other words, you have to average over one wavelength. Okay, once you average over one wavelength, it's the same average, repeating over the entire space. So what is this value over the average value of sine squared over one wavelength? Well, we've studied that before. We know the answer is equal to 1/2. How did we know that so quickly? The trick was, as you probably recall, sine squared and cosine squared, they add up to 1, right? For the same argument, add up to 1, right? And yet, on the other hand, sine squared and cosine squared should have the same average value over one period, right? And therefore, they add up to 1, and they're equal to each other, and therefore the average value of either sine squared or cosine squared over one period is what? Is 1/2. Okay? So, this is 1/2. So I found this to be 1/4 epsilon naught E maximum squared. Okay, meanwhile, what about the magnetic energy? The magnetic energy density UB is equal to 1 over 2 mu naught B maximum squared. Right? Okay. Actually, B maximum squared. And then there is also sine squared. Kx minus omega t with the same exact average value of 1/2. So this is equal to 1/4 divided by mu naught and then B maximum squared. Okay, these two expressions look very different, and yet it is easy to show that they're actually equal to each other. You shouldn't be surprised by this because the symmetry between E and B field says that they should be the same. The only thing that breaks the symmetry of the E and B field is that there is electric charge but no magnetic monopole. But remember, we're doing everything in a vacuum. In a vacuum, there is no electric charge either. Okay, so you completely get rid of this remaining asymmetry between E and B fields. They should exactly behave the same way. They should contribute, for example, the same amount to the electromagnetic energy density carried by the entire wave. How do I show that? Well, we know that B maximum equals E maximum over C, right? So I have UB. Okay, so I have UB over UE. Okay, I'm going to find the ratio. I want to show that the ratio equals 1. Okay, 1/4 cancels out. This is B maximum squared over mu naught, right? That's that, divided by epsilon naught E maximum squared. Now B maximum itself is E maximum over C, right? So you square it, and there is an epsilon naught, mu naught, and there is an E maximum squared. Okay, what is 1 over epsilon naught mu naught anyway? 1 over epsilon naught mu naught. Isn't that C squared? So this is really C squared times E maximum squared over C squared. I just worked this out. And then divided by E maximum squared. See that? That's exactly the one. So UE average equals UB average. In other words, the energy carried by the electromagnetic wave is shared evenly by the electric and the magnetic components, each carrying 50% of the energy. Okay, that is required by the symmetry between E and B. Okay, now with that, I am now able to rewrite the total energy, so the total energy density UEB. Okay, that equals UE plus UB, right? Okay, I can write either of these, either this or that, and times what? Times a factor of 2 because they're equal to each other. Okay, for example, I can write 1/2 epsilon naught E maximum squared. I can also write 1/2 mu naught B maximum squared. Okay, I can do that. Now, there's nothing wrong with that, except on first glance it looks a bit misleading, because this expression seems to say that all you really care is the electric field. You don't have to worry about the magnetic field. It doesn't have to exist. And that one says the other thing around. It says, you only need a magnetic field. In reality, you need both an electric field and the magnetic field. Okay? Now, is there a way I can rewrite either of these so that they become more symmetrical about E and B? So I'm going to include both E and B together in the same expression. Okay, in the same expression. Well, of course, turns out I can easily do that because I'm going to break this, for example, I'm going to break this E maximum here into E maximum times E maximum. And the second E maximum, I'm going to use what? I'm going to use E maximum equals B maximum times C. Alright? So, for example, 1/2 epsilon naught times E maximum times the second E maximum, which is B maximum times C. Right? Of course I can do that. Now, what is C anyway? What is C anyway? C can be written as 1 over epsilon naught squared, 1 over the square root of epsilon naught mu naught, right? So I can write this as 1/2 epsilon naught and then square root of epsilon naught mu naught B maximum E maximum. See, I can do it this way. Okay, and let's see, what do we get? This is 1/2 the square root of epsilon naught mu naught E maximum B maximum. Okay, this is a little bit better because it contains both E maximum and B maximum, so you see the symmetry between E and B. Okay, now what I'm going to do is, I know that this is the average value of the electromagnetic energy density over space. I'm going to multiply this by the volume of the box. Okay, that is the total energy contained within this volume, and all this energy will pass through this window over time t. So therefore, how much power passes through this window? That would be the total energy UEB, which is energy density times the volume of A times CT, right? Cross-sectional area, length CT. And I'm going to divide this by what? By the time it takes for all this energy to pass through, which is T. Okay? So you divide that off, okay? You get UEB average times A times C. Okay? What is this again? This is the total energy passing through this window per unit time. By definition, that is the power that you intercept. Okay. Now, if you use a greater volume, a greater cross-sectional area, you are going to intercept greater amount of power. Okay. What really determines the strength of the wave, as far as energy flow goes, is how much energy, how much power you can intercept per unit area. So what I'm going to do is, I'm going to take this power value, time average power, and I am going to divide this by the cross-sectional area A. So what I'm getting here is a time average value of the power transmitted through a unit cross-sectional area. And that, by definition, is called intensity, I. It is defined as average power divided by the cross-sectional area A, which intercepts the power. Okay, now that is, of course, UEB bar times C. Right? Now UEB is right here, and C is again 1 over the square root of epsilon naught mu naught. Okay, so you work that out. You take this times the square root of epsilon naught cancels, square root of mu naught times the square root of mu naught. You're getting this E maximum B maximum over 2 mu naught. Okay, so this is the expression for the intensity carried by a plane electromagnetic wave, whose amplitude of the electric field is E maximum, whose amplitude of the magnetic field is B maximum. Okay. The reason why you have a factor of 1/2, you can trace it back to the time average. Okay, to the time average. Actually, not the time average, but average over space from here to there. That is why you have that. So when we study a plane electromagnetic wave, we have to deal with sine squared and cosine squared function when you take the energy density, and that's what 1/2 comes up. Okay, so please keep that in mind. Now, as far as the direction of the energy flow, it is the same as the direction of K, right? So E goes this way, B goes that way. So I can actually, if I want, I can actually turn this into a vector. Okay, I can turn this into a vector, I, the energy flow, to be in the direction of E cross B divided by 2 mu naught. This is what? Is a vector whose magnitude equals to intensity of the wave, whose direction is along the direction of propagation. Okay, and again, this 1/2 is only because of the averaging process of the electromagnetic wave over one wavelength.